And I'm very grateful to the organizers for kindly invitations. In this lecture, I want to speak about the lifetime behavior of the fluid motion in 3D exterior domains when the motion of the body is time dependent. Let me start with the setting of the situation. In a viscous fluid, filling the whole space R3. You have a rigid body, which is moving in the fluid in a prescribed way. By taking a frame attached to the rigid bodies, you can reduce a problem in the inertial frame to the equivalent one in the fixed exterior domain, which I denote by capital D. Let me also denote the translational and angular velocities by eta and omega, which in general still time dependent in the frame attached to the body. In the equation of momentum, that is a Navier-Stokes system, the change of frame I have mentioned brings new terms, namely, in addition to the Stokes part, you have the rigid motion, whose coefficient is just a rigid motion. It is given by the translational velocity eta plus the rotational velocity omega exterior product x. This is a drift term. And the other is a 1/2 of the Coriolis force, subject to the solenoidal conditions. And if you like to consider the non-slip boundary conditions, the flow attains the rigid motions there, while the flow is assumed to be at rest at space infinity. The question I'd like to address in this talk is how to analyze the lifetime behavior for this initial value problem when both eta and omega are time dependent. In these non-autonomous situations, so far, two kinds of solutions are constructed. One is unique solutions locally in time for initial data being in the space L3 as usual. And the other is weak solutions of Roulet-Hopf class globally in time for initial data with finite energies. And the local existence theorem was proved by Hansel and Rhandi. Several years ago, while the construction of the weak solution was due to Borges much before in his Habilitationsschrift. And the essential contribution of Hansel-Rhandi is a linear analysis, which I will explain. So to do so, let us drop the nonlinear term. Here. And also let us replace the boundary conditions by the homogeneous one. Zero Dirichlet boundary conditions. And the initial time should be a parameter in linear analysis, which I denote by S. So let us consider this initial value problem for the linearized equations. What should be done, first of all, is a well-posedness of this initial value problem, which is by no means obvious. Hansel and Rhandi, in the same papers, succeeded in the construction of the evolution operators. Denoted by a capital T of Ts. On the solenoidal LQ space, LQ sigma d for every q between 1 and q. And what is remarkable is that they also deduce smoothing action of this evolution operators, LQ, LR smoothing actions, where R is greater than or equal to Q. And the singular behavior of the evolution operator is as usual near the initial time, like minus 3/2 1 over Q minus 1 over R, when the initial velocity is taken from the LQ space. And they also deduce a smoothing action near the initial time of the gradient of the evolution operator as well. And then the singular behavior is, of course, 1/2 mode. The estimate is local, so if when t is less than some finite time and denoted by tau star, then the constant here depends on tau star. I'd like to stress that this result is very non-trivial because corresponding autonomous operators is no longer generators of analytic semigroups. So you cannot apply the general theory of evolution operators developed by Tanabe and Sobolewski. To get around this difficulty, they employed a certain cutoff technique to construct a parametrics by using evolution operators in the whole space and in the bounded domains near the boundaries, and then perform some iteration procedure. Look at their proof. You see that if you impose sorry, I forgot the assumption on the translational and angular velocities. They proved this result provided translational velocity and angular velocity are locally Herder continuous. And when you look at their proof, you can find that if you impose more assumptions like eta and omega are globally Herder continuous. As well as bounded. Then the constant C here in this estimate can be taken uniformly in S and T as long as T minus S less than tau stars. So the result is the starting point of my study, and the question I'd like to address in this lecture is the large-time behavior of these evolution operators as T minus S goes to infinity. The main result of this lecture is the following. Under the same assumptions which I have just mentioned, namely eta and omega are Herder continuous globally in time and bounded. The evolution operators enjoy the LQ-LR decay estimate for all S and T, and the same estimate for the adjoint evolution operator as well. However, only for the evolution operator itself, I mean that I couldn't obtain the optimal rate of decay of the gradient of the evolution operators. Concerning the decay estimate here, it can be taken uniformly in translational velocity and angular velocity, whose norm is less than given constant m, which can be large. Norm consists of the one is the Herder semi-norm, the other is just a L infinity norm. So I mean that the decay constant C depends on m here, but it can be taken uniformly, eta and omega, whose norm is less than m. This is the main theorem of this talk. And the last statement is needed to apply this theorem to the Navier-Stokes because the boundary conditions of the original problem involves the eta and omega, which must be small. And the next question is how to deduce the estimate of the nonlinear term only from the LQ-LR estimate for the evolution operator itself without any pointer's decay of the gradient of the estimate. This is in fact possible and seems to be new to the best of my knowledge. And actually, as a consequence, you can prove the stability of the rest state of the original Navier-Stokes problem. This situation is less interesting than more involved case where there is a non-trivial background state. But what I want to show you is how to deal with the nonlinear term only from the estimate of the evolution operator itself rather than the global existence result itself in the simplest situations. Can I erase? Yeah? Before going to the proof, I should mention the autonomous case in which the evolution operator is just a semigroup. In this case, LQ-LR decay estimate is well developed, and it always plays an important role to discuss the stability of the Navier-Stokes flow. When both eta and omega are equal to 0, in which the linearized system is just a Stokes system, almost optimal result was obtained first by Iwashita. In the sense that his conditions on the summability exponent for the decay with this rate for the gradient of the Stokes semigroup was optimal. In fact, the optimality was made clear by Maremonti and Soronico. Among several more complete results. As for the Oseen semigroup, in which eta is a non-zero constant vector, and omega is absent. Kobayashi and Shibata succeeded in the deduction of the LQ-LR estimate of the Oseen semigroup. For the case of the purely rotating obstacle, in which the omega is a non-zero constant vector, while a translation is absent, the same decay properties was proved by Shibata and myself. Most of the literature rely on the spectral analysis to great extent. But compared to the autonomous case, the spectral analysis does not work well in the general non-autonomous situation. So in this talk, I'll take another way with some quite elementary device to get the result. And the spirit of analysis is somewhat similar to the Stokes paper by Paolo and Soronico. But unlike the Stokes papers, I don't find the useful energy estimate except for the first energy relations. Probably the only fine information is the flow in the whole space R3. It would be the only clue to go on. Actually, the flow in the whole space can be written explicitly in the following way. Let capital phi of Ts is the evolution operators, evolution matrix to the following ordinary differential equations. d phi dt is equal to the minus omega exterior product phi. Then the evolution operators in the whole space for the same linearized equation, which I did not capital U, can be written by the His semigroup in which you make the change of variable by use of this evolution matrix and the translational velocity eta in the following way. Here, inside you have this matrix. Capital T denotes a transpose. So this is the explicit representation formula in the whole space. So as you see, the estimate of the evolution operator in the whole space is the same as for the His semigroup. This is not very surprising because our equation is not artificial. It is exactly derived from the original equation in the inertial frame just by change of the variables. So in the rest of my lecture, I'd like to speak briefly about the proof. As I have just mentioned, everything is fine in the whole space. And therefore, for given initial velocity, which I denote by a, little a, that can be taken from the nice class of functions with solenoidal conditions. It is reasonable to regard the exterior flow as a flow in the whole space plus perturbations. In order to keep the homogeneous boundary conditions, I need a cutoff functions. Phi is a suitable cutoff functions. And also the correction term to recover the solenoidal conditions. Where capital B denotes the so-called Vygotsky operators, namely this second term is a particular solutions of divergence equations. And you can take, if you like, you can take another solutions of the divergence equations as long as it satisfies the fine properties such as the optimal regularity. So you now subtract those terms to get the remaining term, which I denote by V. How can I, maybe here. And then this remaining term, V of t, satisfies the following integral equations in terms of the evolution operator itself. Capital P denotes the Fujita Kato projection. And this function, capital F, is a body force term, which consists of several terms arising from the flow in the whole space. And of course, F has a bounded support. Here, A tilde denotes modifications of the given initial velocity, and it is given by the this formula with use of a cutoff function and the Bogoski operators, whose support is also bounded. And our task is, of course, to investigate the large-time behavior of V of t here, but it is perhaps difficult to deduce directly the decay estimate of V of t because at the beginning, the information about the right-hand side is quite a few. So the strategy is the following. I will try to the uniformly boundedness of the remaining time V of t in the space LR for large time. T minus s is greater than, for instance, 3. Where R is greater than 2. If once you have this uniformly boundedness of V of t for large time for some R greater than 2, then you can show the following lemma. From these assumptions, the evolution operator is uniformly bounded in LR for such R. So by duality, the adjoint evolution operator is also uniformly bounded in LR prime. This combined with Galliard-Nirenberg inequality, as well as the fast energy relations of the adjoint evolution operators, implies a certain differential inequality. So you can solve this differential inequality to obtain that LQ LR decay estimate of the adjoint evolution operators for let me change a little bit the notation. Suppose V of t is uniformly bounded in the space LR0. then the adjoint evolution operator satisfies the LQ LR estimate when Q is greater than R0 prime and R is less than or equal to 2. And by duality, you have also the LQ LR estimate of the evolution operators when R is less than or equal to R0 and Q is greater than or equal to 2. So let us derive the LR boundedness of the remaining term V of t when R is greater than 2. Maybe here this is not so wide. Let me use a big blackboard. So to derive the uniformly boundedness to verify the assumptions of this lemma, probably we would have some advantage of consideration of the following duality formulation. Upsize test functions. Duality formulation of that integral equations. Because you can take the local norm of the adjoint operator here and there, since the support of A tilde and capital F are bounded. However, the only thing we know about the adjoint evolution operator is first energy relations, which follows from the skew symmetry of lower order terms of the adjoint equations. And therefore, it is probably difficult to derive the uniformly boundedness of V for every R greater than 2 directly. And nonetheless, let me try to show the uniformly boundedness when R is greater than 2, but R is close to 2. And if I will succeed, I get better information of the adjoint evolution operators, by use of which I can again try to show the uniformly boundedness of the adjoint evolution operators to obtain the probably better result. So you can repeat this procedure, and you can get more and more step by step. Basically, this is the idea to verify the conditions of the lemma 1. I'll focus the integral from s plus 1 to t minus 1 because the other part is not so difficult. From the body force term here, you have the decay estimate, following decay estimate. Tau minus s to the power minus 3 over 2r, which comes from the LR, L infinity estimate of the solution in the whole space because capital F is compactly supported. On the other hand, you can take the L2 norm of the adjoint evolution operators only in a bounded domains near the boundary. Since the support of F is compact and since R is greater than 2. This decay rate, minus 3 over 2R, is not very strong. Actually, after integrations, this cannot be convergent. However, if you take the square of this decay, just by Helder, then you have a bit advantage. Actually, when R is less than 3, this term is bounded for large time. So you might have some chance to go on. On the other hand, concerning this term, the adjoint evolution operators, it is better to take the gradient. And actually, you can replace a gradient of the evolution operators by the Poincare inequalities because solution of the adjoint system satisfies the homogeneous boundary conditions at the boundary of the exterior domains. So here you have gradient of the adjoint evolution operator square and this is just a situation in which you can use the first energy relations of the adjoint evolution operators. I mean, this inside of the square is bounded from above by the kinetic energy. Here, the upper end of the integral come here. This is opposite to the parabolic equations because the solutions of the adjoint system satisfy the backward problem subject to the final conditions at final time t. So the upper end come here. Then you have the estimate like LR prime norm, R prime is less than 2, LR prime of the test functions. Therefore, you see the following. the remaining term v of t is uniformly bounded. For large time, for r greater than 2 and less than 3. Then by this lemma, by lemma 1, by lemma 1, you have the LQ LR decay estimate of the adjoint evolution operators when Q is greater than 3/2 and R is, of course, less than or equal to 2. Now you can proceed to the next step in which R is greater than 3. From this decay estimate, we have just obtained you have the LR prime L2 estimate of the adjoint evolution operators on account of the semi-group properties. Strictly speaking, backward semi-group property because it satisfies the backward problem, as I have mentioned. And then you can obtain the decay estimate like almost minus 1/4, where epsilon is arbitrarily small. Where R prime is less than 3/2. To apply this decay estimate, as you see, actually we have better information than the previous step in which we know just boundedness of the evolution operators. Although this is a weak decay properties, but we have better information. To apply this decay estimate, it is convenient to split this integral. Yeah. I want to be done of the first blackboard. So, no. Second. It's not so easy. Yeah. This is the second blackboard. No? Yes. Now I have understood. And this is the first one. So up. No, this is the first one. And that is the third one. Okay. So as I have mentioned, let me split the integral into the following two parts. And you can directly apply that decay estimate to the which one? To the former integral. Actually, I do need the dispersion square as I did here. So let us consider the integral from s plus 1 up to half of s plus p. The integrand is the dispersion square. Then you can again utilize the first energy relation of the adjoint evolution operators. As I told you, the upper end of the integral comes here. Come here. Now you can apply the beta information obtained in the first step. So from this part, you have the decay. Like since we have a square here, this term decays like almost 1/2. On the other hand, look at the other part. Since we are now considering the case r is greater than 3, it is growing like 1 minus 3 over r. On the other hand, we have the decay. So there is a dispute between the growing and decay. And as you see, it is uniformly bounded when r is less than 6. Yeah. Look at the other integral. Let us turn to the other integral. Here you have the decay from the body force term. T minus s to the power minus 3 over 2r. And the remaining term is just a gradient of the evolution operators, adjoint evolution operators. So what we have to do is to compute exactly the growth rate of this integral. To this end, the following lemma is quite useful. Fix S and the function z is locally square summable over the interval S infinity. Suppose that the integral, let me assume the positivity of these functions. Suppose that the integral of this function z square from s plus t to s plus 2t decays slowly like t to the minus alpha, where r is less than 1. Then you can compute the integral of z itself up to s plus t. And the conclusion is that it is growing like t to the half of 1 minus alpha. The proof is simply done by splitting this integral diagonally in the following way. And this summation is convergent because alpha is less than 1. So the proof is very simple, but it is quite useful. And let me apply this lemma in our situations. I'm sorry that this S is different from that S, but anyway, we have this information. This gradient of the adjoint evolution operator square decays like minus 1/2 plus 2 epsilon. By use of this lemma, this integral is growing like the one quarter plus epsilon. So there is again a dispute between the decay and this growing rate. And it can be uniformly bounded when r is less than 6. Of course, those situations for both integrals are comparable because this lemma provides the optimal growing rate of this integral. So now we have the better information. Our remaining term is uniformly bounded, provided r is less than 6. As a consequence of the first lemma, we have the LQ, LDK estimate of the adjoint evolution operators, provided Q is greater than 6/5. So having this even better information, even though R is greater than 6, you have the LR prime L2 decay of the adjoint evolution operators like almost minus 1/2. Then you can repeat the same argument as before to get the decay estimate stated in the main theorem. So finally, let me conclude the treatment of the nonlinear term. by the duality formulation, it suffices to consider the following dual term. Here, the gradient comes to the adjoint evolution operators. The psi denotes test functions. Perhaps the only possibility to take the L2 norm here, because the only thing we know is first energy relations of the adjoint evolution operators. So it is reasonable to find the Navier-Stokes flow in the space L4. And as usual, let me take the initial velocity from the L3 space. Then L3, L4 decay is tau to the minus 1/8. So here you have tau to the minus 1/4. So what we have to estimate is the following integral. So the key observation is the following lemma. What I want to say here is that although we don't have a pointwise decay of the gradient of the evolution operators, you have the you can estimate of this integral like here test function should be taken in the space L4/3, whose dual is L4. And then here you have the decay t to the minus 1/8. So that estimate is closed. The idea of this, the proof of this lemma is essentially the same as that of the decay of the evolution operators. I mean, as I did here, we have to split the integral, this integral into two parts. One is up to half of t. The other is the integral from half of t. And one of them can be discussed by combining the first energy relations of the adjoint evolution operators with the main theorem. And then the other part can be discussed by use of the second lemma, as we did here. It works as if we would have a pointwise decay of the gradient of the evolution operators. Maybe I can stop here. Thank you for your attention.
Can you apply it to the user? I have written that you succeeded to improve to get a global solution, even though you do not have any information on the gradient of the same.
Yeah, right.
Therefore, suppose that omega and eta is identical equals 0. Can you apply that?
Identical equals to 0. Yeah. This means that it is just a Stokes system. Yeah.
And therefore, I have feeling that you do not need any information for the gradient.
Yeah. Yes, you can apply this argument. However, of course, the Navier-Stokes solutions by this procedure has less information. Yeah. But you can apply. Yeah.
Roughly speaking, the information for the gradient of adjoint operator is calculated up to L2.
Up to L2, yeah, on account of the just first energy relations.
Therefore, L2 information for the gradient of adjoint symmetry is enough
enough to just get the Navier-Stokes flow, yeah, with some decay properties, but we have less information about the asymptotic behavior.
You assume that the velocities eta and w are given and uniformly bounded, and some c.
Yeah, uniformly bounded and globally held continuous. Yeah, that's all. Yeah.
Uniformly.
Yeah.
Can you get some better decay estimates if, say, both velocities goes to 0 by some rate? Or is it normal for this?
Yeah, but concerning the evolution operator itself, I mean, we don't take the gradient. Then I already got the optimal LQLR decay of the evolution operator. So maybe your question is a possibility that we could get the even gradient.
No, don't speak about gradient, but behavior when time goes to infinity.
Yeah.
Is there some maybe better decay?
Yeah, but our main this is the main sir. So when j is equal to 0, so when I don't take the gradient of the evolution operator, this is the optimal decay. So you cannot improve. Even though eta and omega, for instance, goes to 0 as t tends to infinity. Yeah.